Our session today is Functions and Calculus 3, so quite an advanced module in terms of the manipulation of algebraic expressions. And we are going directly all the way down today to running a biological model. Hopefully you have looked through the materials on the website or in the PDF beforehand, so you'll be familiar with the terminology that we use and with the references that we make throughout our session. Download materials, here's a list. You have a PDF file where there's complete session notes, where all the codes and all the figures that we are generating here during the session will be available for you in a written form, so you can look them up later for your perusal. And we have 3 files with MATLAB code, which is actually worked out solutions. So if you don't follow what we are doing here, you can look up the whole thing afterwards with included comments. So you should be able to do what we mostly do, namely take some existing code and then modify it for our individual purposes. And we comment on the individual files a little bit later. So we start with an introduction that's not now, today will not be a MATLAB exercise, but it's actually how to rearrange algebraically an equation such that you can get meaningful information out of it in the context of a biological model. Our first major exercise will be the gene expression exercise 1.4.4. So we skip over 1.4.1 because that refers to the Hill function, which we actually have done previously 4 weeks ago, that was. So you can look it up there. Now we're going to look into how to modify an existing model, to expand it, and how to interpret the changes that occur due to the modified code. And our final exercise will be on the toggle switch, which is a well-known biological model to describe surprising functionality in gene expression regulation, which is due to nonlinearity in our mechanism, and the nonlinearity will lead to features that are important to know before you think of analyzing your data. And that will bring us, if we have time, I'll do some outlook on what is going to come later on in the module 1. If you have questions, we can take a few minutes to try to answer them, and that will bring us to the end of today's session. So before we go into it, just to mention this, here's a picture from a reference in 2010 in Nature Reviews of Genetics, where the idea of deriving quantitative models is actually originally taken from electrical engineering, where the thinking of electronic circuits has been taken out of its original context and put into the context of biological systems, and specifically in gene expression regulation has proven to be an extremely helpful concept to make good mechanistic assumptions, simulations, and model predictions with a fairly established repertoire of mathematical tools, some of which we are going to introduce today. So, our introductory exercise, and to do this exercise I will now stop sharing my webcam. We'll have that on later. What we are going to do here is to look at an equation that we are given, and we try to interpret the meaning of this equation. Specifically, we want to get a piece of information out of this equation. So how do we go about? So we're given an equation, not surprisingly, has the form of one of the equations in the materials. We have some function called y, and in parentheses it says lowercase t, that is a function that depends on time. It's a temporal dependence of the function y, is actually calculated as the product of a constant, here denoted as y0, and the other factor is the exponent of something which is calculated as minus a constant c times the time that has passed during, for example, an experiment. So here's an equation that you are given, and before you go into actually simulating the equation or plotting the equation with MATLAB, you can just look at the equation from a mathematical point of view and try to guess some of its features. So one of the features is best found out if we know functions of the exponent. So the exponent means that a certain number is raised to a power of something else. The power is given here in this round parentheses and is minus c times t. If that expression here highlighted in yellow is 0, then whatever the exponent is, whatever the number of the exponent is, will be 1. Anything to the power of 0 will be 1. So we know that this function on the left side, y, for a time equal to 0, which will make the exponent equal to 0, will start with nothing but y0 times 1. So it's equal to y0. So we know its starting value right ahead, just looking at this function. And what if t has a very large value? Then we have to consider that t is actually multiplied with minus 1. That's what the minus sign means here. And a minus in the exponents is the same as saying the number of the exponent is actually calculated 1 over. It's the reciprocal value. So that means the larger t gets, the reciprocal value will get successively smaller. So for very large values of t, say t equal infinity, we'll have a number that approaches 0. So we know some of its features, and as you can see here from our title, one of the concerns with such a function is what is the half-life of this function. Half-life will be a measure for the time scale of our model, and time scale means on what time scales do we expect experiments to happen, do we expect changes to happen. So it's an important feature to know. And in order to calculate the half-life here, we go through this brief exercise. We start with the definition of what is actually the half-life. Half-life is the time point of this function when the value of the function y is equal to just half of the initial value. So if the initial value is called y0, then y0 divided by 2 is the concentration where the half concentration or half initial concentration is reached, and the time point when this happens will be called the half time. So what are we going to do to find out the half time analytically or quantitatively in this equation? We're going to substitute this definition, y equal y0 over 2, into our original equation. So it means on the left side where we have yt, we substitute this and we put in y0 over 2. And the right-hand side stays nearly the same, except we say this is true not in all cases, but only in the cases when time is equal to the half-life. So far, nothing really has happened. We have substituted two things into our equation. We've expanded it, so to speak, under certain conditions. Now, if we see that both the left-hand side and the right-hand side of an equation is multiplied with y0, we can divide both sides of the equation by y0 to get rid of it. And we end up with a simplified version of the equation, which is given highlighted in yellow here. Now we can see that what we want to have is an expression where th, the half-life, is isolated on either the left-hand side or the right-hand side of the equation. Now, how do we get there? The obstacle here is the exponent, obviously. We need to get rid of this exponent. How to get rid of it? Well, what is the inverse function that gets rid of the exponent? It's the logarithm. And if the exponent is with the base e, the Euler's number e, 2.7 something, then the corresponding logarithm is the natural logarithm. So what do we do? Both sides of this simplified equation are subject to a logarithm. So the left-hand side is logarithm of 0.5, just the previous division by 2, and the right-hand side, everything is put under the logarithm here in parentheses. Now this simplifies very naturally because logarithm and exponent are inverse function. They cancel each other. So we end up on the right-hand side with some simplified expression, which is minus c times th. And on the left-hand side, we have the negative logarithm of 2, which is the same as the positive logarithm of 0.5. If you want to know more about features of logarithms and exponents, they are all done very explicitly in the mathematical appendix to this session. And now this equation highlighted, need to go back, highlighted in yellow, is easily rearranged. If we want to isolate the half-life, we just put it on one side of the equation, and we end up with the analytic or explicit quantitative expression for the half-life. We calculated, knowing the constant c, we just divide logarithm of 2 by this constant c, and we get the number of the half-life just as we wanted. If we have a constant of c that's equal to 0.1, which is what we're going to do in a second, then we can just do it in MATLAB. The natural logarithm will be log, and we saw that it was logarithm of 2, and we divide that now by 0.1. We can calculate its value explicitly. It should be somewhere the order of 6.9. Make the window clean again. That finishes our initial exercise, and we're now going to go and look at the model of gene expression, which takes as a starting point what is shown here in this slide, namely the original model. And we are going to look at what happens if we expand this original model, put in some new features, what happens to the graphs that we see here, and how we end up with different temporal dynamics of gene expression when we put in different features, meaning assuming different mechanism of the gene expression. Okay, so we are going to do this together. So Rob will join me now.
Hello everyone again.
What is the first thing that we need to do, Rob? Let's have a look in MATLAB at what we actually have as an assignment.
So our assignment, we have a file on the desktop with our assignment in it. So I just made it big enough so you can read everything. Okay.
Right. The assignment says, look at the code which models expression of x. So you need to have looked at the textbook to know what this means, but I guess you're familiar with this. Regulated by a transcription factor y. Now we have a transcription factor y that regulates the expression of x, and we have a system of two equations that are given here in this assignment. They are repeated here, and there's certain values that we are supposed to use for constants g, b, and c, as well as two values for the initial concentrations of those two factors in our assumed situation of gene expression regulation. So what are we supposed to do? In the first sub-question, it says take the code that was given originally in the textbook for this above model and modify one of the equations. So Rob, how would you define this modification? What is happening here actually?
Okay, so we want to change the original equation so that the rate of change of y is now equal to minus c times y. So we first need the code, first need the original code. So I've got that in another file on the desktop. So we could modify it here, but actually I'm just going to copy and paste this into the other window. So I've copied it, and I've pasted it. Okay, so that describes the original model. So we need to start modifying this. So what we did, we need to the rate of change of y. So that's here. We need to change that to be equal to minus cy. Okay, we can do that. Minus. the c is already there, times y. Okay, with initial conditions, with x at x0, that's fine, and y at y0. Okay, so we haven't got that before. So previously we've had y times 0 equal to 0. Now we want that to equal to y0. And it doesn't matter that we haven't defined that yet, because we're about to, because we're looking at this symbolically. So the code we had before should still work. So we asked MATLAB to simplify x and y, and then show us x and y. So if I run this, so I run this script file, now in the main window we should have the results. So here we go. Oh, it's quite big. Just about to see everything there. So I forgot to show you what it looked like before, but we didn't have this same function for y in the original model. So that was the original plot for the previous case, but now we've got a different form for y. Okay, so that's the first part done, I think. You'll agree?
That's the first part done. So we have explicit functions, which are too long to repeat orally here, but we have explicit functions showing us what the solution is. So what it means is now, given these functions, we can use these functions to plot our prediction, namely similarly to what we did in the beginning exercise. If we have an explicit function here called x and y, we can use them to plot our prediction. How is this going to evolve into the future, starting from a time point 0?
So the next part is to plot these concentrations. There's lots of things we could do to get the form of these back into MATLAB. So the moment we've got symbolic equations, which mean that MATLAB is quite happy to deal with abstract things such as b's and c's and x naughts. But actually, we want to plot this we want to integrate this numerically now. So we need to, sorry, let me rephrase that. We need to plot the plot x and y numerically. So we need to tell MATLAB what x and y are equal to. Sorry, what all of the parameters here, c, x0, y0, are equal to. Okay? So we need to do that. We need to use this sims command, and that defines these symbolic. Sorry, Gil, do you help me with this?
Yeah, what I want to say is that we have our solution in a certain way, which is specific. So MATLAB gives them out in a symbolic way. But if, Rob, you say that we want to have them numerically plotted, we can't do that with the symbolic function. So actually, we take the symbolic function that we have and we convert it into an algebraic function. And it's the algebraic function that we'll be able to then plot. We have seen that before. In the first two sessions, we used fplot to do this, so I think we can just try to use fplot again after we have converted the symbolic function into a MATLAB function.
Yeah, so in order to do that, we need to use this MATLAB function, which I'll show you in a second. First of all, we need to define the variables. Sorry. Okay. So we're going to call, sorry, let's start this again. Sorry. So we need to make a new function from our previous solution, which was these two on the screen here. So I'm going to call this my, and I'm going to call this MATLAB function, and I'm interested in what the output of y is. So y was our solution here. And then the remaining commands for this, I'm not going to go into right now. Gerald might have comments.
Yeah, so we're looking first at the factor that is regulating the expression of our gene expression protein of interest, which is X. So we're looking at Y, the regulatory protein, and what we have here is we have it defined as Y, and bars, we define that we have T the time which is in the function, we have y naught, the initial concentration of this factor, and we have c, which is the constant here. And this is given in symbolic expression. Now we need to turn this into the algebraic function my, which is the MATLAB function y, so to speak. And we can see what happens if you execute this.
Okay.
Now you need to define what is y naught, also what is t and what is c. And so I think we need to have symbolic.
So this was what I was typing. Oops, sorry.
Yes, this is what you were trying to say. Symbolic t, y naught.
Sorry.
Initial concentration and our constant, which is called c.
Let's try that again.
And now we have a MATLAB function my at the bottom of this window here. So you can see MATLAB converted it into one of these functions that we used to have like before. We have variables in this function are now t, y naught, and c. So if we want to have that as a function of time, what will we have to do with y0 and c? We will have to define them explicitly. We'll have to assign them values.
Yes.
So let's do that as a next thing. How do we assign values? We now define our function that we're going to plot. Give it some name.
F1, let's say.
For example, our function
F1.
plot, yes.
One, let's, in case we want to call some more.
And then we need to define which of those things that we have is our variable that we're going to look at. So if we want a temporal evolution, we want to have it as a function of time.
Yes.
So time will be our independent variable.
So we use that notation where we have an @ symbol and then brackets with the variables we're interested in
Yes,
inside.
as before. And then we take our function, which is called my, and now we need to specify t is going to be the variable, so we just leave the symbol t there. And then for the value y naught, we have a suggestion at the top of the assignment. It says y naught should be equal to 10.
Here we go, y naught equal to 10. And while we're here, c is equal to 0.1.
And c equal to 0.1. So we need to
back
put that
down in our code, 10 and 0.1.
So we need to specify in that order, right? Because we have said that in previous, that first is time,
T.
Second is initial concentration, third is constant c. So in that order, we define t as our independent variable, y0 as 10, and c as 0.1. And this thing we can plot immediately using fplot.
Okay, so fplot plots a function. So fplot, it was called fy1.
Sub 1, that's our function. We need to define some limits, say
So,
with
comma 0.50, say.
For example, 0.50, and that's
And
closing.
then close the brackets. So that should work, and we should now plot our function.
And we immediately get a plot of this function. So while we haven't labeled it properly here, this is a temporal evolution. That means on the horizontal axis we have time running. And so what can we see here? How would you describe that mathematically?
Well, that looks like some sort of decay, exponential decay.
That looks like exponential decay, which we have looked at previously. So it starts from this initial value of 10 and it goes down to 0, which is not really surprising because, as you can see on the left-hand side of our screen, this is just a thing where we defined the half-life. So if we go back to the plot, will we actually be able to see the half-life? So what was our half-life? If I remember correctly, we found the half-life as 6.9.
Yes.
So how can we look at it? Half-life means that the initial concentration has decayed to half of its value. So 10 divided by 2 is 5.
Could follow that across to about here.
If we go across to the function and
it's quite hard to see, but if you go down,
maybe we can insert a line. If we insert a line from that point at 5 where it crosses the plot, yes, that's approximately where it crosses. And if we do another line and go straight down in a 90-degree angle down, then this should be, if it's correctly done, it should be near 7. So we know the exact value is 6.9, but it looks good, I think. So that would be then the half-life. And it shows you, of course, whatever the time scale is, whether that's seconds or hours or years, the definition of this half-life will then show up and give you a typical time scale over which, in this simple case, half of the original concentration is being consumed according to the model assumption that we have made, namely that the concentration of this regulatory protein Y decays as a function of itself times a certain constant. Yep, that's as far as Y is concerned. Maybe we can leave the plot open, but we now try to look at our function for X. Now the protein of interest, the expression of which was our major interest, and we need to do similar things again, but now expliciting the function for X rather than Y.
Okay, so if you recall, I'm just going to run. So if we go back to our window, we can remember what X was. So this is this long function here that it's a bit hard to see what it is on this sort of MATLAB window. So we nice to plot this, and we'd fulfill the requirements of the question. So we know we've got some things in here that we have to tell MATLAB that we're expecting. So things like the X0 we've already said, and the C we've already said. But now we've got, the Y0 we've already said. Now we've got X0 and G and B, for instance.
Right, so all these things need to be specified so that we can deal with them explicitly.
So we need to tell MATLAB they're symbolic. We want T, we want B, we want X0, we want C, we want G, and we want Y0. So that covers everything.
Yep.
And now, exactly as before, we want to convert this expression into a MATLAB function. So this expression here, we want to convert into a MATLAB function of T, B, X0, C, G, and Y0. So as I did before, we want to call this M of X for MATLAB function, say, of X. Use the MATLAB function, and now we're going to give it X as our symbolic equation. We're going to use the command vars, and then we're going to give it an array with T, B, X0, C, G, and Y0.
So we now have 6 things to deal with explicitly. We have time plus 5 other values that we need to be aware of when we're doing an algebraic function. Yes? Okay.
So because we only want to deal with the time, really, when we're plotting, again, I think we should make a helper function. Again called, say, now small f, x1. And we're going to use the same notation as before. We're going to do alpha t to say that we still want it to be a function of t. Our thing we're interested in is mx, We still want to leave t unknown, and then we're going to set all of the other variables. So in this case, we're going to do 1, 0.1, another 0.1, 1, and 10.
Maybe we can go up to the assignment and see where these values come from.
Yes, so I think these were from the original question. So C is 0.1
Yes.
as before, X was 0.1, but now we've got Y0 as 10, B is 1, and G is 1. And they should fit in the right order.
But we have, yes.
They should fit in the right order. Here we are, inside this function.
Okay, so we have taken what the assignment told us to do, and with this line we should be able to produce our function that will be able to use the specific values for the initial conditions and the constants and plot this function as a function of time. Right, so let's use fplot again. That's very similar to what we had above.
Now we need to give it f of x. Need to give it some limits. I'm going to go to 0 and 50 again.
And we have the same limits as previously.
And that should run. So,
and if you want to give it a different color, maybe it's a little bit easier to distinguish. So red would be shorthand is R. And if we put that into single quotes, that's the way to assign a color to this line that connects the points of the function.
So if you want them on the same plot as well, we have to do hold on previously to plotting the second line. Okay, now if I run this, Oh dear.
You have called it
Oh,
the
I've called
wrong
it,
way.
sorry.
It's actually sub 1, so
Then let's try that. Go back to the figure. Ah, brilliant. So we've now got a red line on here too. So that's the function of x as well as y. Okay, I hope you can all see that. So the next part of the question is, Gail, would you read it for me?
yes, the next part of the question was question number 5. How has modifying dy dt changed the behavior of x as a function of time? So maybe we can go back to this plot of the original function. What happened previously was that from a low value, the concentration of this factor x, the expression, the protein of interest, increases in a continuous fashion.
In no matter what our value of c, so it just increases all the time.
It just increases, and the reason is that y increases. Previously, y used to increase linearly, so x, which is regulated by y, also kept increasing in a certain fashion. But now the picture has changed. If we go back to our current plot shows you in blue y is now starting from originally a high value. So we have a large amount of this regulatory protein y, but it decays exponentially until eventually it's 0. So the concentration of x can't just keep rising infinitely. It starts rising while a lot of y is there, but as y decreases, it actually reaches a maximum point.
Yes.
So there's a point where it starts to shrink rather than grow, and it means we get this hump function, the single hump function, where x initially rises, goes to a maximum, and then decays. And similarly, because it's regulated by y, just as y goes to 0, also x will be going to 0. And we'll have in this, if our experiment works according to this model, then at long times we'll find no concentration of either protein. Neither protein will be present, but of course that depends on our assumptions. So we might have other assumptions later to bring it back again. You can see how there's some value in putting in the expansion of the model, with showing that with a certain exponential decay in the other regulatory protein, we see a pulse of x, if you wish. So it's coming up suddenly, but then decays again. And especially the important thing is the half time or the half-life of y now defines the width of our pulse. Right? So if you're thinking in biological terms, if we have a decaying regulatory protein, that defines the width of this pulse of the red curve here, which means for a certain time there will be a large amount of gene expression of X available, but after that it will decay and will no longer be available. This is important, of course, for things like timing. Timing events, setting on certain cascade or changing metabolic pathways, or responding to signaling information from external agonists to receptors. We can see such things very frequently in gene expression, that they are not continuous but actually come in a pulsatile fashion. So here's a very, very simple, a very basic way of putting it, but we have shown how these assumptions can be used with analyzing the equations, solving the equations, and then plotting the predictions, which is the function of time explicitly, if models are not too difficult. It concludes our exercise. I just bring back our camera again. So what we have now is this problem that while it would be good to have simple mechanisms everywhere in the world, biology is not always simple. And one example where biology is not too simple, but also not too complicated to be looked at in this introductory context that we're doing today, is we're using a model that is already nonlinear. So it defies the explicit calculations of all its trajectories beforehand, as we have done in this very simple gene expression regulation model. But we know there's a remedy out of this, namely we can use something called numerical integration. Numeric integration will be a major tool for many, many studies that whoever is working with biological models will need to do. More than mathematical handling, it's numerical studies that we are doing today because we don't have access to analytic solutions in general. So let's look at this toggle function. That was our last assignment for this session, and let's look at it in a way that maybe makes sense and get an introduction how numerical integration works. We have to clean our screen a little bit, get rid of all the things that we have, and let's first look at what we have as an assignment. So here's the assignment. So we are actually given a new model.
Yes.
So everybody should be aware with the old toggle model that we have introduced in the materials. But please now take a look. So Rob has already opened it, and we're given a new function, and there's two things to comment on this. So first of all, we are not going to start to do everything from zero.
So, I mean, often in real sort of modeling, you're given functions that other people have developed, and your task is more to manipulate them and modify them than to come up with them on their own in the first place. So in this task, we've been given this toggle function here, but we've actually not been given the script to integrate it. So we need to be able to simulate the system before we can do anything else, I think.
Okay, let's try to take a look whether the original thing works.
Okay.
So let's look at the script that takes this current function here, which is called toggle. And to do this, you're going to do that separately, Rob?
Yeah, so the first thing I'd like to point out that we've been given this function file. So this is a file that defines a function toggle. So we could come into MATLAB, and because, I'll just make this a bit smaller, and because we know what this function looks like, we could just run this in MATLAB. So we could type toggle into this window. This is assuming that the function's saved in the right place, but we can discuss that later if necessary. We know that it takes a time and it takes a y, and then looking into this function, y must have two elements.
Mm-hmm.
So we
could have two variables.
So we could set a time of 1 and a y with 0 and 1, say, and then that will run, and that will give us an answer. But that's not really what we're interested in, because this is a differential equation. So we're defining du, dt, and dv, dt. And so we're actually not interested in those, but we're interested in what happens sort of over time as we vary our u and v.
Mm-hmm. And that's what we call solving the differential equation, so to speak.
And because they're more complicated than before, we need to do that numerically rather than analytically. So the first thing we need to do is now make a new file. I'm going to save this as toggle switch onto the desktop as well. So this is going to be the function. This is going to be the script file that I use to run the function in this other window. Okay. So again, what do we need to know? Well, we need to know how long we want to run this for.
Right. As is explained in the materials, we need to give it a time span. So it starts from a certain time, which is defined here as 0, and goes to a certain time, which is upper limit is 15. And in addition to that, we need to define initial conditions.
So they're normally called something like y0. And the ones I've been given are 0.1 and 1.
And this is the case because we have two variables. We need to define two initial conditions. What previously was x0, y0 is now here our 0.1 and 1.0, two values for the initial conditions. Now, how can we run a simulation?
So I happen to know there's this function called ODE45 that numerically integrates the other function. So the syntax in this is a bit different to I think anything you've seen before. So what we need to do is say we call the function ODE45, and then we need to give it a function. So not just a number, a variable, we need to actually give it a function. The way we do that is by prepending the function name with an at. The function we know is called toggle, and we know MATLAB knows what toggle is because when we ran it in the window before, it worked. It didn't complain that it couldn't find that function. We need to give it the time span, and we need to give it the initial conditions. And of course, we need to collect the output. And the output has two components. It has a time component, and it has the y component. So that will actually be a two-dimensional array. It'll be a
Right, so this is now have to be careful. Y is not the same as previously a single variable, but Y is actually the collection of all variables. So if we have two variables, this array Y will give us out the temporal evolution of two different things. Of the first variable, which is called U, I think, in the toggle context, and the second variable, which is called V in the toggle model.
Yeah. So effectively what's happening is every time point we're running the toggle command on some new U and V, and it's giving us two answers.
Yeah.
So this Y will have two answers for every time point. Okay, so the only other thing we want to do is we want to be able to plot this. So I'm just going to do a simple plot T, Y. Okay? So now we can run this. Well, let's save it first and then run. Oh, that worked. That's always good to see. So our plot comes up. I'm not quite sure about which line is which is U and which is V.
Typically, as a default, blue is the first variable. So if that is called U, that would be our first variable. U would be as a blue line, and the green is the second standard color assigned if you don't define them specifically.
Okay.
So maybe you put in a legend to remember that and call the blue U.
Can I do that from here?
Yeah. Call it U, and the second will be V.
Okay, great.
So that's how the original worked, and we are now asked to take this model and to turn it into a variation of this model, into a different thing that has some components in common, but some components are different.
Yes, so recall the question wanted us to, let's find the question. I think we've got it here. So recall the question said, we want to, another toggle switch can be modeled with the equations du by dt equals alpha 1 divided by an exponential of beta times v minus u, and similarly for the dv dt. What have you got over here?
So as in the toggle switch, there is mutual inhibition. V inhibits U and U inhibits Y. So the function is different, but the concept of inhibition stays the same.
So we've got, this is different here, so these two lines need to be changed. So we could change it here, but that's not really best practice. The best thing to do would be to copy this now into another new file. I'm going to get rid of that old file, close it, and put it somewhere safe. Okay. And I'm going to call this new function file, say toggle mod.
Or modified, maybe.
Yeah, that's what I was thinking. Oh, happens to already exist. Oh, I'm in the wrong place. I'm sorry. I'm going to put this on the desktop so that we definitely know what MATLAB knows where I am. Okay, so that's great. So we've made a new function called toggle mod, which is sitting on our desktop now. MATLAB seems to be complaining about something. And so function name toggle is known to MATLAB by its file name toggle mod. Well, MATLAB requires that functions and the files therein have the same name. So before we had toggle in the file toggle, now we've got toggle mod in the file toggle mod. Okay, so I'm going to save that. So that's great. Okay, so go back to the original toggle switch script file. So previously we called toggle. Now all we want to do is call toggle mod. Oh, I forgot to actually modify the file. I'm sorry. So I'm going to open toggle mod again. So actually what I did was not remember to modify this. So if you recall, we wanted to change this equation to exp beta times v, and this to exp gamma times u. And save that. Okay? But also we wanted to change the values of beta and gamma to 3 and 3.
Yeah.
Okay? So what I did before was copy across this function, but I forgot to change it. And so we would have got exactly the same result as before, which may have made us think that we forgot to do something, but Gerald reminded me, so that's great.
Okay, so we have our new function file, our modified function file, and now we can use a script as before, use the script to run this new function file and see what happens.
So the only thing I needed to do here was change toggle to toggle mod because we're using a different function. And now I can just run this. Oh, it looks a bit different, yes. What would you say, Gerald? So I can't quite, so we recall there being a bit of a lump here before, now there's a very small lump.
Yes, so what we can see here is that qualitatively similar to before, if we start with a low value for this variable u, it actually never comes up to a high value at all. It stays at a low value, which means its inhibition of the other value will be low, and then the other protein, say, concentration will be able to rise and assume a high value throughout the time that we simulate here. So that's what we can see here. And this is, of course, a behavior which is just similar to what we had seen in the original toggle model. The reason being actually very simple, and you can do that yourself, checking that the functions actually are not so dissimilar. So while mathematically there are different ways of writing it, the functions themselves do a very similar shape. And that means qualitatively we'll reproduce the behavior from before, but quantitatively we have changes. And for the rest of the exercise, which we don't need to do here manually before you are now asked to change the initial conditions. Or maybe we should just do it.
It won't take very long.
Why not try it? Change the initial conditions for these two. Yeah, we can just do it. Change the u to a large value. Here a suggestion would be 5. And the v to a value of 4, for example. So there's different initial conditions now. And if we hold on the previous plot,
okay, hold on,
and run the simulation again and plot into the same figure.
Oh, that is different.
Then we can see that now with changed initial conditions, we do get a different output. And what you can see here is that we're starting with a fairly large amount of the protein U, which is the blue curve, in this case at 5, a high value. Although it decreases, it seems to be wanting to decay to 0, actually because we chose an initial condition in V, which is even smaller than the initial condition in U. U actually can manage to go through a trough and start to rise, and now it is the winner this time. It assumes the high value that was previously assumed by Y, meaning that there's a certain symmetry here, that it's either U or Y, it's either U or V which wins, but no, we cannot have the situation that both are expressed simultaneously at high levels. So this is a case where the cross interaction between these two regulatory proteins just helps us to make sure that we have either one or the other expressed, but not both at the same time. We'll talk about this in subsequent sessions a little bit more in detail. Let's just summarize what we have seen so far. We have seen ways of explicitly making predictions using explicit temporal functions to predict into the future what happens with certain concentrations of our regulatory proteins. But we have seen that when we have nonlinear models like the one that you see here displayed on the screen, we need to resort to another technique which is not explicit function, but is to get the function out of the solution of a differential equation by means of numerical integration. We can get very similarly predictions. That's what we want. We want to have the time frame predicted. We have certain temporal scales predicted. For example, here the time it takes for both concentrations to arrive at their asymptotic value or at their final value, and so on. So there's loads of things that we can do with these things. And let me see what the time is like. We still have a few minutes left. So one thing that we could try is to just as not really as an exercise for you, but just as a prediction. How will you go about with such models later on? Of course, you will not stay at this stage running it over and over again, but you will want to go and modify it further. Namely, bring in further assumptions that you have made. Is the file still somewhere here? Where is that function? Toggle switch. Is that what it was called? Where's the function file?
Is it the toggle mod or toggle?
Toggle modified. It's this thing here. But you will do further modifications to this. So I just want to mention one modification that you could do is that you can modify your function file such that you simulate perturbations, which we'll do at a later time point. And you could do perturbations such that for certain time points, you change certain values of parameters. If you assume that something is happening in your system, you can do this in a way, for example, using an if condition and say if t is larger than 30, whatever time units you then have, you can make a change and say, for example, there will be a different situation happening as this parameter alpha 1 will assume a different value, whereas it's 10, maybe it will assume a smaller value. Right, if I call this correctly, alpha 1. And if I conclude this, what this will do is it will run the simulation up to a time called 30 with the parameters assumed up here. So alpha 1 will have a value of 10, but then all of a sudden, from time 30 on, will have a different value, which you can specify. Means you can then incorporate perturbations like changing the experimental conditions. Say you flush your experiment, if you have that somehow in a culture, you flush that with some different substances to change, to make changes to how gene expression is regulated. And we can just, for the fun of it, we can just look what will happen if we have this model changed. What will happen to our simulation? We'll just try to run it.
I don't think it ran. I might be wrong.
Didn't run. So let's see our final thing. And sorry, I don't need to take away the axis. And we can see that in this case, it didn't make a lot of a difference that our value of u is going up to the high point. So are we actually running this thing here? Alpha 1 equal to 1. So make alpha 1 equal to 0. Have it changed, saved, and then run our plot again. I don't see that actually.
Let's just try refreshing everything. Is it because because we're only running it up to time point 15? And
so we can't see this. There was an error here. We are running to a time called 15, but we say we make the perturbation at time equal to 30. So that's why we don't see it. So let me now do a simulation of this here. And what can we see here? I don't see the difference here.
I think it may just be due to our choice of alpha 1. Let's have a look if perturbing alpha 2 will make a difference. I'm not sure what's going on there, why we're not seeing any.
So we have to finish because we're at the end of the session. This would be the way to include a perturbation if we want to make modifications during the time course of the simulation further down the road. Thank you for watching us today.
Thank you.
Download the files that you see on the materials page. You have worked out solutions there. You can try to copy the code, modify the code, and we'll be back next time with more explicit description of how to use numerical simulations to set up a mechanism that we assume about a biological system and have it run as a prediction and as a way of experimenting digitally before we do any wet lab experiments.